The last talk today will be given by Tasho Kaletha. He's going to tell us about the double coverage of tori and the local Langlands correspondence.
Okay, thank you very much for the kind invitation. I want to talk about a topic today that I discussed also in my talk in the fall at the Princeton University IIS number theory seminar. But I would like to present it in a somewhat different way and emphasize not just the construction of the local Langlands correspondence for supercuspidal parameters, but also a characterization of that correspondence that is of spectral nature and that also works uniformly in some sense for all local fields, including the real numbers. So I'll begin by a formulation of the local Langlands correspondence, which will be something that is familiar undoubtedly to everybody. So it will serve mostly to fix notation. So let us start with a local field, F, that I also allow to be the real numbers. The complex numbers will not play much of a role because I'll be interested in discrete series representations. And I'm going to write gamma for the Galois group relative to some fixed separable closure, and W for the Weil group. And I'll also use the Weil-Deligne group, at least in the beginning, and I'll denote it by W prime. And G will be a connected reductive group defined over F. And let me consider a discrete Langlands parameter starting from the Weil-Deligne group. So what do we expect in this situation? We expect, first of all, to have a finite set that I'm going to denote by pi sub phi of G, finite set of essentially discrete series irreducible representations of the group G of F. And we also expect, if G is quasi-split, that there is a unique generic member in this finite set where this curly W is some fixed Whittaker datum, so a fixed Borel subgroup together with a generic character of its unipotent radical. And there should be a unique generic representation in this finite set of representations. And finally, we would like to have an injection or even a bijection when F is non-Archimedean from this finite set into the irreducible representations of a certain finite group. And those irreducible representations that transform under a certain central subgroup by a fixed character. So what are these things? We have this finite group. This group S phi plus, one can think of basically as the centralizer of the image of the parameter in the dual group. And in some cases, this is literally what it is. And in this centralizer, we have the center of the dual group, the Galois fixed points. So there is a corresponding close related subgroup in here. And on this finite group, we have the character zeta. And what this character does is it basically measures how far away the group G is from being quasi-split. When the group G is quasi-split, then this character is trivial. And when the group is not quasi-split, then this character measures the difference between G and the quasi-split inner form. This is basically a Tate-Nakayama version of the Galois cohomology of G. So these are roughly the expectations that we have every time we have a discrete Langlands parameters. But these expectations alone do not really characterize the set of representations pi phi G or this map here that I've written under point 3. So what I would like to do is give now a characterization which will be of a spectral nature of this local Langlands correspondence for discrete parameters under certain assumptions. And this characterization is supposed to pin down uniquely both the set of representations, pi phi g, and the map to this set of irreducible representations of the centralizer. I want to note here that there is a different approach to what I'm going to present. Again, of spectral nature, and it's in a recent paper due to Bertoloni-Melli and Yukis, and they use what are called Schulze-Shinn functions. So they give a characterization for certain kinds of groups that are in some way related to Shimura varieties. So I'm going to give a different a characterization of a different nature, but I wanted to mention that there is another approach to it as well. So what is the characterization that I would like to talk about? It has two steps. The first step is very well known, and it comes from the theory of endoscopy. So I'm going to be fairly brief and skip most details. So let's consider an element in this centralizer group. We can assume that it is semi-simple. And then from this, we can form the corresponding virtual character from the L packet. We're going to sum over all representations in this finite set of representations. And we're going to take their Harish-Chandra characters. And as a weight in front of each Harish-Chandra character, we're going to take the representation rho sub pi, which corresponds to pi under this injection here. And we're going to take its trace evaluated at the element S that we have of this group, which will be some complex number. And in the special case that this little element S is 1, I would like to introduce a slightly different notation because it plays a special role. So what do we expect here? First of all, we expect that this virtual character for the special element 1 be a stable distribution, which means that it is invariant not just under conjugation. All of the summands of it are invariant under conjugation, being characters of representations, but also invariant under stable conjugation, which is roughly conjugation by points in the algebraic closure. And the second expectation tells us something about the general S's. So then this virtual character evaluated at some test function is supposed to be related to the stable character on an endoscopic group. So here H is the endoscopic group associated to the parameter S and the parameter phi in the element S, and FH is the transfer of F. Now I'm skipping all details. I'm being very vague here. I'm not explaining what is an endoscopic group and how is it constructed and what is the transfer. And the reason I'm not explaining this is because this is a well-known and well-documented part of the theory. So I don't want to focus on that. But the point I want to make here is the following, that if this is true, then characterizing the local Langlands correspondence reduces to characterizing this stable distribution. Because if we knew this stable distribution, then this identity tells us something about all of these distributions. And then this identity here, via Fourier inversion along this finite group here, is going to recover all the individual characters in the finite L packet. And so we're going to know what the L packet itself is. So this endoscopic character identity reduces characterizing the local Langlands correspondence to the following step 2, which is give a formula for the stable character in terms of the parameter phi. And this is the thing that I want to focus on today. So in order to give a formula for the stable character, we're going to use a device that is the double cover of an algebraic torus. And it is a fairly elementary device, but it turns out to be quite useful. It was introduced in the work of Adams and Vaughan for a tori over the real numbers in the 1990s. And I'm going to give now a construction that generalizes their work to an arbitrary local field. And this construction in turns can be seen in some sense as a reinterpretation of computations that were done by Langlands and Schaustat already. So the construction goes like this. Let S be an F torus, and consider given a finite subset of its character module that does not contain 0 and is stable under the Galois group and the group ±1, where the Galois group acts in a natural way on the character module of the torus, and ±1 acts by multiplication. Now, given such a finite set, we obtain two things. The first thing that we obtain is a double cover of the group of rational points of this torus. And the second thing that we obtain is an L group for this double cover, which means an extension of the Galois group by the dual torus. That's not the usual L group of the torus S, which would be the semi-direct product of the dual torus by the Galois group. It will be some other kind of an extension. Now, instead of giving you the precise construction of this double cover and the extension, I want to give you the two key examples of this construction, and then the general construction is made out of those two examples in a certain, not particularly difficult way. So the examples are the following. They are about the one-dimensional tori. So we have the split one-dimensional torus, just the multiplicative group. In that case, the double cover of the rational points is just a split double cover. So the multiplicative group of the field F, direct product ±1. And the L group is also the split extension, just the dual torus, which maybe I should write is simply C cross times the Galois group. And the second one-dimensional torus is one that is anisotropic and splits over some quadratic extension that I want to denote E over F. So I'm going to write it a restriction of scalars from E over F of the multiplicative group, but the part of it that is the kernel of the norm down to the multiplicative group. In that situation, the double cover is the following thing. So the rational points of the torus are the subgroup of the multiplicative group of the torus consisting of elements whose norm is 1. And we have a surjective map from the multiplicative group of this quadratic extension that sends every element to the quotient of it by its Galois conjugate. And the kernel of that map is the multiplicative group of the field F. And since F is a local field and we have a quadratic extension, we have a quadratic character of that smaller field F cross. And when we form the push out of this diagram, we obtain the double cover. And so depending on what the local field F is, this double cover can be canonically split or non-canonically split or not split at all. And the L group of this double cover, for this, one can check quite easily that if we conclude the second Galois cohomology group for the Galois group of this quadratic extension, valued in C cross, but where the Galois group acts by inversion on C cross, this is a 2-element group. And the L group corresponds to the non-trivial element. So it is a non-split extension. So these are just two examples. But in the general case, we have a local Langlands correspondence for this double cover. That is, we have a bijection between L parameters into this double cover. So homomorphisms from the Weyer group into the L group, modulo conjugation by the dual torus, and genuine characters of the double cover, which means characters of this group SF tilde, whose restriction to ±1 is non-trivial. And moreover, over the real numbers, this construction recovers a construction due to Adams and Vaughan, namely the so-called row cover, or maybe more precisely the row sub I cover, which is a version of the row cover that was introduced a little bit later. So using this double cover, we can now go and give a formula for the stable character associated to a discrete Langlands parameter that is going to characterize the corresponding L packet. But this is going to be done under certain assumptions. So the assumptions I have in mind are the following. So let's take a discrete parameter. And assume the following. The first and main assumption is that this parameter is trivial on the SO2Ps of the Weil-Deligne group. Really, it's a parameter starting from the Weil group and not from the Weil-Deligne group. The second assumption is that the group G splits over a tame extension. The third assumption is that the characteristic of the ground field is 0. And the fourth assumption is that the residue characteristic is large enough. Among these assumptions, the latter two I feel can be relaxed substantially, but I haven't carefully thought about this. So this will be something that I'll address in the future. Whereas those two assumptions are more crucial, and in particular, this first assumption in my mind cannot be removed in that situation. So in that situation, what is the formula for the stable character? Well, if we start with a parameter, then it is fairly easy to extract from this an elliptic maximal torus S in the group G, well defined up to stable conjugacy. Now that we have this elliptic maximal torus, we have an ambient root system, the absolute root system of the group G with respect to this maximal torus. And we can take this as the set R in the construction of the double cover. So this set R is going to give us a double cover of this torus. And one of the key properties of this double cover is that there is a canonical L embedding from the L group of the double cover into the L group of G. That's the first very useful feature of this double cover. And this canonical L embedding factors the parameter and gives us a genuine character theta tilde of this double cover. Okay, so far everything is canonical. From the discrete parameter under these assumptions, we obtained a elliptic maximal torus, a double cover of it, and a genuine character of this double cover. And now from this genuine double cover, we can extract the following, from this genuine character, we can extract the following data. We can take this genuine character and we can restrict it to the pro-unipotent radical of this torus. The thing is that as soon as P is not equal to 2, and this is certainly part of my assumption that P is large enough, the double cover splits canonically over the pro-unipotent radical, and that's an elementary fact because the pro-unipotent radical is a pro-P group and the kernel of the double cover is a ±1. So if I restrict this character to the pro-unipotent radical and compose it with the exponential map, I now have a character of a lattice of the Lie algebra, and I can explain it as a linear form on this Lie algebra. If I fix an additive character of the base field, I will convert the character on the Lie algebra to a linear form. So here, lambda is an additive character, and X is an element in the dual Lie algebra. There are certain details that I'm sweeping under the rug related to depth 0, but more or less, this is how one obtains this element X. And with this data, we're basically ready to provide the formula for the stable character. So we're going to evaluate the stable character on some sufficiently regular semi-simple element. I assume that it is compact modulo the center. Otherwise, the formula is going to return 0. And under this assumption, there is a topological Jordan decomposition of this element, again, modulo the center. So if you ignore the words modulo center, let's say you assume that the group is semi-simple, all this means is that we've written this regular semi-simple element gamma as a commuting product of one element whose order is finite and prime to p, that's gamma 0, and another element whose order is pro p. And now that we have broken up the element, here is the formula for the stable character. The stable character for phi is going to be given as follows. Let me define the centralizer of the finite order prime to p element in G to be J. The formula for the character is the following. It's a certain sign called the Cotwit sign of this reductive group J. Then I have a root number of a virtual Artin representation of degree 0, which is obtained as follows. You take the minimal Levy subgroups of the quasi-split uniforms of G and J. Those are tori of the same rank. And you take their character modules and complexify them. Each of those is an Artin representation of the Galois group of the same dimension. So their virtual difference is a degree 0 virtual Artin representation whose root number we can take relative to the additive character lambda. And then we take the sum over all different ways to embed the torus S into J up to stable conjugacy. Now the element gamma 0 is in the center of J, and we can pull it back via such an embedding into the torus. And then we can evaluate it as follows. We take the genuine character, theta tilde, which is a character on the double cover of the torus, and we multiply it by a certain genuine function. The product descends to a function on the torus, and we evaluate this element gamma 0 there. This is the contribution of the topologically semi-simple part. The contribution of the topologically unipotent part is going to be the Fourier transform of a certain stable orbital integral given by this element X, which was in the dual Lie algebra of S, and now we have moved it to the dual Lie algebra of J, and that allows us to form an orbital integral on that dual Lie, on the Lie algebra. And in there, we feed the topologically unipotent part under the logarithm. So this is the formula. This is the conjectural formula for the stable character associated to this parameter phi. And this conjectural formula is very much influenced by work of Lawrence Bice that I'm going to mention in a few moments on the character formulas for supracuspidal representations. Now, I can give the explicit formula for this genuine function. This is not a conjectural object. There is an explicit formula for it, but I don't know if it's going to make anybody happy. I can do it at the end of the talk if you would like me, but for now, maybe I'm going to instead make the following remark. Let's consider the special case where gamma itself is topologically semi-simple, so it's equals to gamma 0. Then the formula simplifies. First of all, this J becomes just the torus S, and this sign disappears. We still have the root number here, and then the index of the summation simply becomes the rational points in the Weil group. Of course, we still have this genuine function here. And of course, and then there is no contribution from a topologic unipotent part. And if you look at this, this looks very much like the Weil character formula, or very much like the formula for the stable character of a real discrete series L packet. So in other words, this works over R as well. And it gives, if you unwind things correctly, gives the exact formula for the real discrete series L packet associated to the corresponding discrete parameter. And from that point of view, you now see that this genuine function, when multiplied by this explicit root number, what it does is it gives the complex argument of the Weil discriminant. The absolute value of the Weil discriminant is, of course, well defined for any local field, but the complex argument of the Weil discriminant is something only well defined over the real numbers. Over the p-adic numbers, the result, the Weil discriminant will be a p-adic number, and it's not clear what its complex argument is. And so it is this genuine function here that basically gives you the complex argument. Maybe I should say that this genuine function, it takes values just in plus minus 1. So it really is a sign, and this sign is the sign of the Weil discriminant p-adically, or make sense of that, modulo this root number. Okay, so this is the formula. Now, with this, we have a conjectural characterization of the local Langlands correspondence. And so the next thing I want to do is go into the construction. So the first step would be the construction of the L packet. How does one construct the L packet? The finitely many representations whose stable character is going to meet this formula here. So let me tell you the ingredients of this construction. The construction is going to be completely explicit. That is, starting from a parameter, you can explicitly write down each individual representation. The ingredients for this are the following. First of all, it's JKU's construction from 2001 of supercuspidal representations. So JKU's construction roughly takes the following kind of data. It's a tower of D plus 1 many reductive groups that are twisted Levy subgroups. So they're Levy subgroups defined over the base field of parabolic subgroups that may not themselves be defined over the base field. And then there is a sequence of linear characters, one on each twisted Levy subgroup. And then there is a depth zero supercuspidal representation of the smallest of these twisted Levy subgroups. And so from this, you construct a supercuspidal representation of G of F, which is irreducible if and only if this depth 0 pi minus 1 itself is irreducible. This construction is exhaustive. That is, it produces all supercuspidal representations. This is, well, it's exhaustive when P does not divide the order of the Weil group. This is a result of Finson from published just this year, generalizing earlier work of Kim from 2007. And I'm sure Jessica explained all of this. So the next part of this construction is you can think of Hughes construction as taking the depth 0 representations as a black box and producing all positive depth representations. So understanding the depth 0 representations was done by Moy and Prasad, work from the 1990s. And they explain that a depth 0 a supercuspidal representation is obtained by the following data: a point in the Bruhatitz building. I need to give myself a little bit more room here. A point in the Bruhatitz building together with an irreducible representation rho of a finite group of Lie type associated to this point X. And that finite group of Lie type is most often disconnected. And so what this irreducible representation, the property that it's supposed to have is that when we restrict it, to the neutral component of this finite group of Lie type that this is cuspidal, or it has a cuspidal constituent, but then all of its constituents will be cuspidal because they're on orbit. And now using this, we can make the following definition. We're going to define pi, the representation coming out of use construction, to be regular or non-singular if and only if this representation pi minus 1 is related via Moy-Prasad theory to a representation rho, which itself is regular or non-singular Deligne-Lustig induction. What regular and non-singular means has been defined by Deligne and Lustig as a notion of a character of a torus of a finite group of Lie type. Regular in their language actually meant general position, and it means that there is no non-trivial Weyl element that fixes the character. And non-singular was a root theoretic condition that meant that the character is non-trivial on any co-root. So after this definition, there is a classification result that I proved in a paper that was published about a year and a half ago. And the classification results stated that the set of regular supercuspidal representations is in 1-to-1 correspondence with a set of pairs, S and theta, up to conjugation by the rational points in the group, where S is an elliptic maximal torus, and theta is a character on this elliptic maximal torus that is regular. And here regular is very similar to the definition of Deligne and Lustig, but it's from the point of view of the p-adic group rather than the finite group of Lie type. And the same kind of character parametrization also works in the non-singular case, with one essential difference that we have to discuss in a moment, that one has to allow these representations to be reducible and has to control their reducibility in a certain way. But modulo that, the characterization is exactly the same. Now theta is non-singular instead of regular. And the next crucial piece to this is the character formula for supercuspidal representations arising from use construction. So this character formula was obtained in a work of Adler and Spice from 2009, and then the Bacher and Spice from 2018. And then Spice, I should put a question mark or maybe say draft. This is work that's essentially completed, and I expect it will be publicized this coming summer. And then also my work from 2019, which interprets the roots of unity in the character formulas provided by the other papers in a way that I presented up here, namely using this the Kottwitz sign and this root number and so forth. Now, this character formula applies to a individual supercuspidal representation produced from use construction. Let me not write down the formula. It again has a number of details that I'm not sure people really want to see, but you know, at the end of the talk, if somebody is interested in those details, I'm happy to discuss them. But in order to make the character formula work, we need to add another piece, which is my recent work with Finsen and Spice on a twisted U construction. Namely, as Jessica explained in her talk, there were errors in the paper of JKU originally. And these errors, in principle, broke the proof that use construction produces supercuspidal representations. And the way they broke the proof is by breaking certain intertwining properties. And while Finsen was able to give an alternative proof that use construction does produce supercuspidal representations without the need to be modified, the intertwining properties are indeed incorrect, but they're crucially used in the derivation of the character formula here. And so in order for the derivation of the character formula to work, these intertwining properties needed to be restored. And they didn't hold for the original construction, but we were able to find a twist of the original construction by a certain sign character that was quite subtle to define and gave us a lot of trouble, but eventually we were able to sort it out. And by twisting the U construction by the sign character, we restored the intertwining properties, and that in turn allowed the computation of the character in Spice's work to proceed. So using all of these inputs, what now happens is that we can index regular or more generally non-singular, possibly reducible representations by pairs of an elliptic maximal torus and a character of its double cover. The passage between the torus, character of the torus here, and characters of the double cover happens within the character formula. And now that we have done this, the construction of the L packet is complete. It goes as follows. We're going to take all embeddings of S into G. Remember that S was a maximal torus of G, but only well-defined up to stable conjugacy. So there is a stable conjugacy class of embeddings of S into G, and that decomposes into multiple rational conjugacy classes. And for each of those, we have a representation given by these points 1 to 5 that I outlined. In the regular case, this representation is irreducible, so we just take it and it's a constituent of the L packet. And in the non-singular case, this representation becomes reducible, so we take its set of irreducible components, which I'm going to indicate by these square brackets here. And so that is the definition of the L packet. The next thing I would like to talk about is, yes. Question? Oh, okay, I thought I heard something. The next thing I want to talk about is the internal structure of this L packet. If you allow me to scroll up, I'll remind you what our expectations were. Have an L packet, have a unique generic member in it, and have this bijection, since now we're in the p-adic case. So I've explained to you what this set is. And now I want to explain to you what this bijection is. And then I can go on to discussing this part here. I should say that step 2 is by now complete. That is, we have constructed the packet, and the way it was constructed was precisely so that the formula that I wrote down for its stable character is, Does somebody have a question?
Does somebody have a question?
Oh, am I hearing myself?
Oh, am I hearing?
I guess I'm hearing myself. I don't know. There seems to be some feedback. Okay.
I'm going to Gopal's Zoom.
Okay. Okay.
So maybe there also seems to be some chat here. I see, yes. I don't know, can the person overseeing the Zoom do something about it?
Do something about it.
All right, so I'm going to explain next this map here, and after I've explained this map, I'm going to talk about this. So far, we have constructed this, and accept my assurance that the formula that I've written for this S theta phi is indeed the correct formula that comes out.
Correct formula that comes out.
Okay. Now, how does the internal structure work? Well, there's two cases. The easy case is when phi is regular. Phi is regular, I'm going to give you a simplified definition, which is a little stronger than regular. And that definition says that the centralizer of the image of inertia is in the dual group is abelian. The actual definition of regular is a little bit more complicated and slightly less restrictive. When phi is regular, what happens is that each, as I already mentioned verbally, each representation is irreducible. So by construction, this L packet is enumerated precisely by the set of embeddings of this torus S into G. So that means, but there is a cohomological description of this. I forgot one very important piece before I go into the internal structure. Namely, I forgot to write the proposition that there exists a unique generic member in here. So this G contains a unique W generic member, of course, when G is quasi-split. This is proved using the character formula because work of Moglin and Vautz-Bourget tells us how to detect genericity using the local character expansion. And since we now have the character formula, we can consider the local character expansion and compare it to our character formula, and out pops out this proposition. Okay.
Have you fixed a Whittaker model here, or?
Yes, so when I write W generic, I mean for a given fixed Whittaker model, there is a unique generic representation. And we know how it changes when we move the Whittaker model. There is a simple recipe to tell us. So then this is in one-to-one correspondence with the set of embeddings of S into G, which is a simple Galois cohomological device. That's the kernel of the Galois cohomology of S into the Galois cohomology of G. I'm secretly using here Vaughan's pure inner form language because I don't want to overcomplicate things more. But now in principle, this group acts simply transitively on this set, but this existence and uniqueness of generic constituent, together with putting all inner forms in a coherent way together, which I'm also sweeping under the rug, breaks this torsor and makes it into a bijection. But now basic Tate-Nakayama duality explains to us that this is the same as the characters of the component group of the Galois fixed points of the dual torus, precisely those which under the Galois fixed points in the center of the dual group transform under or restrict to the character that determines G as an inner form of its quasi-split form. While on the other hand, the embedding of the L group of this double cover into the L group of G identifies the Galois fixed points of the dual torus with the centralizer of the parameter. And with this, the internal structure of the packet in this simple case of a regular parameter is complete. But what happens when the parameter is not regular? Well, then the situation becomes much more subtle. Why? Because first of all, this representation corresponding to each S and theta is usually reducible. And secondly, because the centralizer of the parameter now is not simply the Galois fixed points in the dual torus, but in fact, there is an extension. The Galois fixed points in the dual torus are part of it, and the other part is given by rational points in the Weil group, the part that fixes this character of the double cover. In the regular case, no Weil element fixes the character of the double cover, which is how we recovered the previous case. And in both, and usually this group is going to be non-abelian, so its set of irreducible representations is going to become more complicated. And we have to deal with multiplicities in both of these points. So the irreducible constituents here can occur with higher multiplicity, and the same can happen with representations here. So how do we deal with this? Well, we first reduce to depth 0, and then to a problem over the finite field. Let me not explain how these reductions work because I'm running short on time. So let me only explain to you the problem over the finite field and how it is solved. So the problem over the finite field is the following. G is a reductive group over the finite field and usually disconnected, and that's crucial. Why? Because it is this reductive group, if I scroll up again to Moy-Prasad theory, it is this reductive group coming from Bruhat-Titz theory, and that reductive group is usually disconnected. We have a elliptic maximal torus. We have to make sense of what this exactly means when the group is disconnected, but my setting is a little bit more specific, and there is a natural notion of that. And there is a character of this torus, which is non-singular in the sense of Deligne-Lustig when restricted to the neutral component of this torus. The problem is now understand the irreducible constituents of the Deligne-Lustig induction for this disconnected group. Now, this problem was studied for connected groups by Lustig. And Lustig proves the following theorem in the connected case. When G is connected, this representation is multiplicity free. Of course, it is cuspidal because the character is non-singular. And the constituents are a torsor for a certain finite abelian group. Namely, you take the Weil group, take its rational points, take the stabilizer in there of the character, and take the Pontryagin dual. There is a canonical torsor structure under this abelian group for the constituents of this Deligne-Lustig induction. And the problem that we're facing is that this fails when G becomes disconnected. Both the multiplicity statement fails and the torsor structure, of course, also fails. So the question then is, how are we going to rectify this problem? And the idea is to use intertwining operators. Because intertwining operators are what is used to decompose parabolic induction over a local field or over a finite field. And why not, using the idea that Deligne-Lustig induction is in some way analogous to parabolic induction, apply this idea here as well. So intertwining operators in the classical theory are usually indexed by elements of the Weil group. So let us fix an element in the normalizer that also stabilizes this point theta. Then let's consider the Deligne-Lustig variety for some Borel subgroup B. Let me call it YB. Multiplication on the right gives me an isomorphism to a Deligne-Lustig variety for the conjugate Borel group. And now I want to come back. And in the classical theory, this is done by integration or summation over the part of the unipotent radical where the two Borel subgroups disagree. But in this geometric situation, this is done by work of Bonafé, Datt, and Rouquier, who consider a following kind of correspondence diagram. They define a certain variety analogous to the Deligne-Lustig variety called the linking variety that depends on two Borel subgroups, and a closed subvariety which becomes a bundle over the original Deligne-Lustig variety with affine fibers. Fibers are affine spaces. And on the linking variety, we can switch to two Borel subgroups at the expense of applying Frobenius to one of them. And then we have a similar correspondence there as well. And one of the main theorems in the work of Bonafé, Datt, and Rouquier, I think this was Rouquier, I think this was in 2007, was that this gives an isomorphism on compactly supported cohomology once you take theta isotypic component. And so that allows us to get an intertwining operator on the cohomology of this Deligne-Lustig variety, which is what realizes this representation. And a problem as in the classical case, is that these intertwining operators do not compose well. If you compose two of them, you don't get the intertwining operator for the product of the two normalizing elements. And one can check rather easily that this problem is of scalar nature. Up to a scalar, this identity holds. And now the question becomes, can we rescale the intertwining operators? Can we renormalize them so that this identity holds? And indeed, this turns out to be the case. So the solution is to prove a cohomology vanishing statement that implies that there exists a normalization. And this is very analogous to the classical case where Langlands proposed a canonical normalization, but the best we have so far is a result of Arthur that assures that there exists some normalization, which may or may not be Langlands's, except that in this case, we don't even have a conjectural canonical normalization. So using this, we get an analog of the Harish-Chandra basis theorem, which tells us that the constituents of this Deligne-Lustig induction are in one-to-one correspondence with the irreducible representations of the normalizer, namely those whose restriction to the torus is theta isotypic, and this preserves multiplicities. And this is really the key. So now we need to relate this to the dual side, but since I'm out of time, I'll skip this part. And instead, I'm just going to take 1 minute to formulate two results, namely about the final thing, namely step 1, endoscopic character identities. It's a theorem in our recent work with Vincent and Spice that these hold for all endoscopic elements that come from the dual torus, which are all endoscopic elements in the regular case, but not quite all endoscopic elements in the non-regular case. For the rest, it's work in progress. And finally, let me advertise a result of my graduate student, David Schwein, who proved that the Hiraga, Ichino, Ikeda formal degree conjecture holds for these packets when phi is regular. And he's currently working on the general case. So let me stop here. I'm sorry I ran a few minutes over, and see if anybody has questions.
Okay, let's thank Tasho for the great talk. Are there any questions?
So as far as I understood, this double cover was there so you could make some sort of canonical L embedding. Previously you were choosing non-canonical ones, but when you make the L packet, you still have to make these non-canonical choices. Like, is there any way to?
No, there are no. What do you mean? I don't think there are any non-canonical choices when you make the L packet.
Well, don't you take an L embedding of LS to LG?
No. I'm using the canonical L embedding from the double cover, and I'm using the character of the double cover that is canonically given to me by the parameter.
Okay. How does that?
Yeah, maybe that will let's look at the real case, and maybe that would help with the situation. So in the real case, a discrete series representation over R corresponds to its, or let's say the group is semi-simple, so it corresponds to its infinitesimal character mu, which is not integral, but it is regular. So it gives you a Weil chamber. So it gives you a row, half sum of the positive roots. And then you can write this mu as rho plus lambda, and lambda is now integral, but possibly not regular. So there is a well-defined passage from a character of the double cover to a character of the torus. And in almost all cases, this lambda is going to be regular itself. And so it will determine the row, and you can go back. Only in very few cases when you're close to the wall, the mu is the more primordial thing than the lambda. And in our situation, something very similar happens. These assumptions here that I outlined Where did they go? I believe these assumptions make it so that we are in the situations where you can pass between theta tilde and theta, just like in the way you can pass between mu and lambda. But I believe once you start weakening these assumptions here, the theta tilde will become the more primordial thing, and it's not going to specify theta. But under these assumptions, you can go back between theta and theta tilde, just like we can go back between the mu and the lambda.
I see, thanks. And but so in the PI case, how did that work? How do you go from theta tilde to theta?
Yeah, so that is related to, let's see, where did it go? Here, so you get this x, and from this x, you get certain information that allows you to write this a tilde, that I didn't write down the precise formula for it, but that same information also allows you to write down a not just a genuine function, but also something else, which is a genuine character of the double cover, which is a very, very slim, it contains very little information. Its values are either in ±1 or at most in 4th roots of unity. And you can multiply this theta tilde that you're given, the canonical thing, by this very slimmed down genuine character. And that brings you down. And you can think of this very slimmed down genuine character as some kind of funky version of this rho that is given to you by this mu. And conversely, in the regular case, this lambda will also give you the rho. And that regularity, I believe, is exactly, where did it go? The fact that this double cover splits over the pro-nipotent radical, which comes because P is not equal to 2. When you try it and pull off this in a residue characteristic 2, this will not work anymore. But also, use construction doesn't work for P equals to 2. And so I think you'll start seeing that if you want to formulate some kind of version of use construction, you're going to be forced to use characters of the double cover to begin with. Whereas now, because P is not equal to 2, you kind of get away with it slightly unnaturally by using this back and forth passage that allows you to do that.
Okay, thanks.
Are there any other questions?
Can I ask, well, first, down question, just something I missed, I guess. So in the very beginning of your constructions, you said that your parameter allows, defines an elliptic torus with a character. Can you say again how this?
Sure. So the way the elliptic torus works is, well, it's a multi-step procedure, but the first thing is you look at the image of wild inertia and you take the centralizer of wild inertia in here, and you check that this is a Levy subgroup of this complex group. This Levy subgroup will be normalized by the entire parameter, by the way it's defined. So that allows you to actually give it a rational structure, and that would give you an entire L group for the Levy. And the way things are set up, your parameter is now going to factor through this Levy and be essentially of depth 0, because wild inertia is going to go into the center. So let's imagine that you now have, and moreover, you can identify this as a twisted Levy into the group G up to stable conjugation. So imagining now that the parameter is depth 0, what you do is you take a topological generator of tame inertia, and then you move it using the parameter into this L group. And you can check that this is a regular automorphism of M hat. So this topological generator of wild inertia becomes a regular auto of M hat. And semi-simple, regular semi-simple automorphism. What the fixed point, the connected fixed points of a regular semi-simple automorphism are a torus, and a torus of a very special kind. It's not maximal necessarily, but it's one whose centralizer is a maximal torus. And that is now a maximal torus in M hat, hence a maximal torus in G hat. And by the way it is constructed, it is again normalized by the entire parameter. So that gives it a rational structure that makes it into the dual torus of a torus of your group. But that torus of your group is only well-defined up to stable conjugacy, and that's the torus.
And another question, if I may, is sort of much more open-ended. So like there's this assumption that phi restricted to SL2 is trivial. And do you envision any generalization relaxing this assumption?
This is the big question mark in my mind. I'm hoping that there will be something, but at the moment, I have nothing intelligent to say about this. I think this is a much harder problem because there's recent conjectures that explain to us that this is precisely the situation in which the L packet contains some, definitely contains non-supercuspidal discrete series representations. It may or may not contain supercuspidal representations, but it certainly contains non-supercuspidal discrete series representations. And those are a big blind spot in our understanding of, at least explicitly, of representations. We don't know how to properly construct them. We don't know how to parameterize them. We don't know what their character look like. We know very little. Lustig, of course, has done work exactly in this situation for unipotent depth zero representations, and he did this by using Heck algebras. And it's possible, and this has been further studied by people like Reeder and Solefeld and Optam and others. And they all use the approach of Heck algebras, which I don't know how much it gives information, say, about characters. So as far as I know, in those works, there are no study about characters and character relations. So I mean, depending on your definition of envision, I envision that something may be done, but if you ask me how, I don't know at the moment.
Thank you.
Any other questions for Tasho? Okay, if no, let's thank Tasho again.
Thank you for your attention.